Hello everyone. We are going to talk about VSEPR, which is an acronym for Valence Shell Electron Pair Repulsion Theory. Let's take a quick moment to parse that and see what exactly that means. So we know what a valence shell is, right? That's the outermost shell of an atom, and it's where you find the valence electrons. Okay, so valence shell, we know what that means. Electron pair, well, that is a pair of electrons. Um, and then repulsion means to push things away. So valence shell electron pair repulsion theory is a theory that describes how electron pairs repel one another, the electron pairs in a valence shell repel one another to help a molecule take its shape. So what we're really going to be talking about here is the shape of molecules. Now, when we draw a structure for a molecule on the whiteboard or on a piece of paper, it's a two-dimensional structure, right? Because it's flat. The paper or the whiteboard is flat. But of course, the molecule isn't really two-dimensional, it's three-dimensional. And the structure or the configuration that a molecule takes is driven, at least in large part, by its electron pairs in the valence shell because they push each other away. Electrons are negatively charged and they don't want to be near other negatively charged entities, so they push each other away, they repel each other, and that interplay of the electron pairs and different components of the molecule all combine to give a molecule its three-dimensional shape. So we're going to look at how molecules adjust their shapes so that the valence electron pairs can be as far apart as possible. That's really what drives the shape of a covalent compound. So there are I think 5 of these shapes that we're going to look at, and here's what you need to know for each of them. You need to know the name of the shape. Sometimes we will have bond angles, so that'll be, I'll point to it when we get to it, but that's the distance or the degrees between two constituents or two things that are attached to a central atom. Again, we'll see what that is in a second. And then an example of each shape. All right, so these are the 3 pieces that you want to try to get for each of the different molecular shapes we're going to talk about. Let's take a look at our first one. The first is called, the name of the shape is tetrahedral. And tetra means 4, and of course, so a tetrahedral is where you've got a central atom, which in this particular example is carbon, with 4 constituents, 4 things attached to the central carbon. All right, so this example is the common name for this is methane, but we should call it carbon tetrahydride, right? Based on the naming that we just learned about naming of covalent compounds, but everybody calls this methane. So the methane is an example of a tetrahedral compound, and the angles between any 2 constituents, so between these 2 constituents, or between these 2, or between these 2, similarly in this picture between like here and here, the bond angle is 109.5 degrees. So those are the 3 things that you need to get from this: the name tetrahedral, the bond angle 109.5, and the example methane or CH4. And it looks like this. The second shape that we're going to discuss is called pyramidal. Okay, now in the previous example there weren't any unshared pairs. So carbon has 4 valence electrons. It gets 4 additional electrons by sharing with hydrogen. There's no unshared pairs. And so that's why it has a tetrahedral shape. Here, for molecules that take a pyramidal shape, there is an unshared pair of electrons. And that unshared pair, this non-bonding pair of electrons, repels the covalent bonding pairs, pushing them away. And so let's take a look at an example. Here is an example of NH3, which is commonly called ammonia, but we would call it nitrogen trihydride. So in this molecule, the central atom is nitrogen, and there are 3 things attached to it. Okay, 3 hydrogen atoms in this case are attached to this central atom, and there's a shared pair of electrons that make up each of these covalent bonds. But if you remember, for it's trying to have, or the goal is to satisfy the octet rule. So there will be two electrons here, two electrons here, two electrons here. That's 6. The other two are an unbonded, a non-bonding or unshared pair of electrons, and they reside right here. And these unshared electron pair push away or repel the 3 covalently bonded electron pairs, and the result is that there's a pyramidal or pyramid-like shape for an ammonia molecule that we see here. So and the bond angles between these constituents are 107 degrees. All right. So 107 degrees. Example is NH3. The shape is pyramidal. The next shape we want to take a look at is called bent triatomic. All right. And in these types of molecules, there are multiple unshared pairs or non-binding pairs of electrons. And the example that we're going to look at here is water. So in water, we have an oxygen and attached to 2 hydrogens. So here's 1 and here's 2. And of course, again, oxygen is trying to satisfy the octet rule. So here are 2 electrons and 2 electrons for oxygen. That means there are 4 more, 2 here and 2 here. I'm not they don't show up in this picture because they're just this only shows atoms still. So 2 unshared or non-bonding pairs of electrons right here and right here on the oxygen atom. Those unshared pairs really strongly repel each other and the bonding pairs here and here. The result is that this molecule takes a bent triatomic state with a bond angle between these 2 hydrogens of 105 degrees. And of course, the example is water. So that's our bent triatomic example. The next one is called linear triatomic. And this one's kind of easier to see because it's linear. The bond angles here are 180 degrees. In other words, this angle is 180 degrees. So here's your central atom, which in this particular example is carbon. And attached to the carbon are 2 oxygen atoms. Here's 1 and here's 2. And we're satisfying our octet rule because these are double bonds this time, although it doesn't really show it in the way these figures are set up. But there's a double covalent bond here and a double covalent bond here. So carbon has its 8 electrons around it, and all is good with the world. So the name for this shape is linear triatomic. The example is carbon dioxide, and the angle is 180 degrees. All right.